Hello and welcome back to the Math and Physics podcast. This is the fifth episode. I'm Parker.
And I am Ray, and we welcome you to an episode featuring our Math 137 professor, Mihai.
Hello.
All right.
So how are you today, Mihai? How are you?
I'm good. How are you guys?
We're doing
Fantastic.
great.
How's your quarantine been so far?
It's not been too bad. It's been okay. I mean, I stay at home most of the time anyway, so it's not that different for me, I guess. Other
Mhm.
than when we transitioned online with the teaching, that was a bit different. But now that that's over, there isn't really much difference, I don't think.
Right. You weren't doing online lectures, right?
Um, so I was sort of doing unofficial online lectures, I guess. So I had just they were basically running as office hours, but it turned out that most of the times people just wanted me to walk through the slides, so that's sort of what I ended up doing. So
Okay.
it was sort of like a lecture, but it was officially an office hour.
Okay. Sweet. I never actually I don't think I went to office hours
I do not think I
during
went to office
yeah.
hours once.
I went to the math learning center. That was actually pretty useful. Um but yeah, should we get into the interview?
I think we can.
Rayon, you want to go first?
Sure. Okay. So let's start with the most basic question. So we know that Mihai is a professor in 137 in U of T, which is a mathematics class based not solely but mainly on proofs. So Mihai, I just want to ask you a kind of vague question, but do you think proofs are important? And if you do, well, why? Why do you think proofs are so important in math and not just the computation?
Oh, well, that's a great question. Well, I suppose it's that mathematicians like to know not just what things are true, but why they're true, and I guess the main emphasis of a proof is to verify that something is true, and it sort of I guess the nice special thing about math is that you can get that absolute certainty, which you sort of don't get in other disciplines, I guess. So that's something that's um, really important about a proof, and it also sort of forces you to solidify your understanding of something, because you have to essentially, a proof has to explain exactly why the thing you're claiming is true. And so once you've sort of filtered a proof through your own brain, you can sort of say with absolute certainty that you know why that particular thing is true. And I guess math is nice for that reason.
Makes sense. Makes sense. Okay, so now that we've got through the fact that proofs are important, how
Mm-hmm.
about well, I don't really know if you have one, but do you have like a favorite proof or a theorem, or maybe like this is my favorite one, or are they just all equal?
I think I have a favorite one, I guess, that I could say. There's one. It's called Cantor's Theorem, and
Okay.
basically it's this sort of proof that pops up in a lot of different places, but I really like the argument of it. It's called like the diagonal argument. So uh, it's sort of like so the theorem itself proves that the cardinality, which is like the size of a set, of the cardinality of the power set of any set is strictly larger than the cardinality of the original set. And it basically does this by constructing a new set and asking, like, constructing a set of all elements where it says the elements are elements of the sets it constructs, or something like that. That's probably wrong, but I mean, it's something like that. And then it ends up being like, it's sort of like Russell's paradox, when like you construct this, that's sort of based on that, where you construct this thing and you ask the question, is the set containing all sets a set, and you get this sort of contradiction. And it's sort of like that, I guess. It's like, or you can, here, maybe this is an easier way to say it. um, you can ask, like, so you can talk about different sizes of infinity, and you can ask, if you look at all the infinite sequences of zeros and ones, so take a sequence and suppose it only has zeros and ones, and you can say, how many such sequences are there? And if you suppose that there are only countably many, so as many as the natural numbers, then you can prove that you can construct a new sequence that isn't a part of those that you were originally considering, by basically constructing a new sequence going down the diagonal of this sort of matrix of sequences that you have. Yeah.
Wow.
Anyway, I did a terrible job of explaining that, because it's actually a very, very nice, like, it's almost like a pictorial proof. Like, you don't even have to really know, like, you could show it to someone in high school and they would totally get it.
Right,
And
right.
yeah, I was actually going to maybe do it on the last day of 137, but
Oh,
we didn't
that
have a class.
yeah, that didn't happen. Yeah, so I'm not totally sure I like understood everything you said there, but yeah.
I don't think I understood what.
All right, so if you were to talk to someone that was going into 137, what would be your best piece of advice
Hmm.
for someone who's like never done proofs before?
Well, I guess to make sure you watch all the videos. Watch all the videos before coming to class. And, there are lots of times in the videos where there's a pause and it says, okay, so try that out for yourself. And it's always a good idea that you do that. You should always try that. And take the um, opportunities given in class to work on something seriously. So they're not a test to see if you can do something right or not. They're supposed to help develop your understanding of something, and it's absolutely okay if you don't get it and you're totally lost and you make lots of mistakes and you don't know how to start and stuff. That's what the instructor's there for, and you should ask questions. And I mean, basically, that's the instructors in 137 aren't there to criticize you or to judge you or anything like this. And so oftentimes I feel sometimes students, they want to um, work on something, but they don't know how to start, and so they get nervous. But you shouldn't get nervous, because the instructors are there to help you, and you should just give it your best shot. Because sort of in high school, I guess, you do these questions and you're always afraid to be wrong in high school, because usually when a teacher asks you something, it's because they want to know if you know the answer or not. But here it's not really like that, so you should really feel comfortable. You should basically forget about the fact that you have to be right all the time when you're doing math. I guess that's what I mean. And just be okay to it's okay to be wrong, and that's how you learn, and that's how you develop, especially with things like proofwriting,
Yeah,
I guess.
that's great. Because we talked about this, we talked about this earlier, I think on like the first episode of the podcast.
I watched your episodes of the podcast, by the way. They were very
Oh wow!
interesting.
Thank you, Sam.
Oh,
Thank you.
thank you. But yeah, we talked about how me and Ray have never gone like into like doing proofs prior to coming to U of T. And
Mm-hmm.
so like the first half of the first semester was super confusing to us because we'd never done like epsilon delta or things like that. So yeah, we were pretty lost. But I think by the time the second semester came around, we had a better grip on doing or constructing our proofs, I think.
We were a lot more confident in the second semester with the exam and pretty much everything, because I think of how much we learned in especially how confident we got with proofs. I think that's what's more important. Once we started getting used to them, I think we really started getting used to them, and 137 became a little bit easier. I think, Parker, because like the midterms, like we actually did well on them. we did pretty well
Yeah.
on the final assessments. So
Yeah,
I think personally it became easier, which is good.
on the well, I think it was third problem set, the limit one, we got like a
Oh
38%,
no,
and
don't
we
remind
thought
me.
we did so well on it. But yeah, we pulled it back in the second half though.
Yeah, that's true. Very true.
Yeah, so I did a little bit of research before starting the podcast, and I saw that you were working on something called Cstar algebras, which I was super confused as soon as I like opened Wikipedia. So is there like a simple way of explaining what you're doing there?
Well, let's see. So maybe the sort of simplest thing I can think of saying is, have you guys taken linear algebra, either 223 or
Yeah.
224?
Yeah, 223.
Okay, so there are like these things called like vector spaces. Do you do that in 223, or do you just talk about Rn? Well, Rn is a vector space, so that's fine. And you have these matrices, right? And
Yeah.
matrices can act on a vector, if you know what I mean. Like you
Yeah.
can take a matrix and multiply a vector by a matrix, and then you get another vector. So
Yeah.
the matrix is like a linear transformation. I don't know if you heard
Yeah,
that term,
we've
but
done that.
okay, great. So now the thing that makes linear algebra kind of unique, I guess, is that like mainly these vector spaces you're looking at in 223 and stuff, you're always talking about finite dimensional things. Okay, so you can think about sort of looking at linear maps between spaces that aren't finite dimensional. So they're infinite dimensional. And because of this, you have approximations coming in. So you have sort of like, I guess, analysis or calculus being mixed with something like infinite dimensional algebra. And you get sort of like this branch of math called functional analysis. And you get these linear operators, but operating on these things called Hilbert spaces. And a C-star algebra is just it's a type of subset of these bounded linear operators. I guess that's the best, easiest explanation I can think of. And then,
Did you get anything right?
so I mean, and then people ask all kinds of questions, like what do these um, C-star algebras look like? Or like an example of a C-star algebra is the complex numbers. That's a very basic C-star algebra.
Okay.
So you already know a C-star algebra.
Yeah.
And another example is like the set of all n by n matrices over the complex numbers. That's another C-star algebra. So they're just, and then people ask all kinds of questions. They want to understand them. They want to classify them. They want to know when two C-star algebras are the same and when two C-star algebras are different and things like this. So
That's super interesting. I mean, like I've yet to go into like linear maps and things like that, but I do find like the what's it called, like the categories interesting.
mm-hmm.
Hey, so Mihai, so is the C-star algebra stuff you're doing, is it for like your thesis for your PhD, or is it just you're just doing it cuz?
Yeah, it is. It's for my thesis. So basically, when you if you do a master's, like normally when you do a master's, you take some graduate courses and then you do sort of a mini project during the summer after that. But the project is pretty small and it can be you sort of work with a faculty member on a sort of micro 4-month project. And then for your PhD, the first year you also take courses. And then after that, you spend about 3 or 4 or 5 years working on a thesis in some particular area, I guess. So I chose to work in C-star algebras. That's typically how it works.
So the first year of your PhD program, was that like hard or was it just like, okay, like what differentiates your first year PhD from, let's say, fourth year math of undergrad, or let's say master's level math? Like what's the difference?
There are a certain number of courses that you have to take in grad school, so master's and
Mhm.
PhD, which are sort of like core courses. So you have to take them and you have to get a certain grade in them. But it's pretty much uh, a natural extension of the courses you've been taking in undergrad. It's just sort of more contemporary material or more modern material, sort of packed at a more accelerated rate. But
Wow.
I guess it's sort of what you're explaining, where with 137, the first and second term, after you sort of got the epsilon delta proofs, then things involving epsilon delta proofs made a bit more sense. And so it's sort of like that, like once you do a fourth year math course, you're sort of naturally prepared to do the graduate courses. In fact, a lot of them are cross-listed with fourth year courses anyway. So there, and between the master's courses and the PhD courses, there really isn't much difference, at least in terms of the core courses. Then there are select topics courses, which you would do if you, once you've picked your particular field, you might take a specific course in your particular field, where you'll pretty much be only with like 5 other people that are also interested in that particular area, let's say.
Okay, so after your PhD, so are you looking to complete it this year or soon? Or
Well, let's say maybe within the next like full year sometime maybe,
okay,
or at
okay,
most a little, like, so before September 2021, I would hope, if that makes sense. So by
okay,
the end of next academic year.
and
Okay.
and after your PhD program, let's say you finish, right? You're all done with your math and you have a PhD in math. Then what will you do after? Like, what is the future of someone who is in pure math? Like, what does it look like? No, because I think Parker and I were talking about this the other day, where we're like, oh, like in physics, we can go into this, we can go into that, because both of us are currently in physics. And
Mhm.
I was just wondering, well, in math, well, once again, I'm not trying to. I'm probably just not biased towards math. Maybe that's why, but I don't really know what the future looks like for someone who has a math degree. So maybe you could help clear that up.
Yeah, I don't even know if I know what the future looks like, but I guess it really depends. So some people, they if they want to stay in academia, they'll try to get a postdoc somewhere, or which is basically like um, you get funding for a year or two to work with, to like try to publish more papers in a particular, in like your area of expertise, and you'll work with a faculty member, but it won't be as uh, guided as the PhD would be, because you're basically on your own more. And so that's one option, and you could do that. You could try to apply for a professorship, and normally that takes 2 or 3 postdocs. Normally, not always, but so that's typically the academic route. Or you could um, sort of go, now a lot of people are going down the teaching academic route, so they want to basically become teaching professors, and so they'll focus more on teaching or math education rather than math research. And then there are those people that want to go to industry, or whatever it is that they want to do that is unrelated to academia, because they've been in the PhD program and they've had enough of it, and um, they just want to do something else, I guess. And they can get all kinds of jobs, I would imagine. But it's not like there is a clear cut, there isn't really a clear cut application of pure math. Like it's more just like there isn't a clear cut avenue, I guess I should say. So it totally depends on the person and what their plans are. But those are some of the ones I can think of.
Right. Yeah. Did you take physics in high school or university?
Um, I did take physics in high school. I took it in grade 11, and I got a terrible mark. I, I got the worst mark you can get while
Oh,
still passing the course.
Oh
And
wow.
but then I took physics in university and I got an A plus, but just the first year physics. So that's my
Okay.
extended knowledge of physics.
Right, right.
And
Because oh, go
mm,
ahead.
no, I was just gonna blabber on with the. I
Okay.
wasn't gonna say any, no content.
I was gonna say that because physics is like kind of like a natural extension to mathematics. So it would be interesting if like you had like second year, third year knowledge in physics, because we talk about math and physics on this podcast, so
Mm-hmm.
anything goes. But yeah. Let me see here. Um, about your experience teaching at U of T. What do you think was the hardest part?
Like hardest part of being a teacher at U of T,
Yeah.
I, maybe walking in the room with like 230 people the first time. um, but that was like maybe a bit nerve-wracking for 10 or 15 minutes. I guess that was pretty hard. But then it got really nice, and I mean, once you sort of don't realize that anymore once you sort of get into it, and it becomes a real joy. I love teaching. I mean, that's my favorite thing. So, well, I was just saying that. So once you get into it and you sort of start to feel the energy of the room, it becomes really exhilarating and fun and a real joy to be a part of. So you sort of forget about the 230 people, and it becomes just like a whole experience, I guess, or something. But I guess that would have been the most I wouldn't call it difficult. I would just say that um, the biggest challenge, I guess, like walking into
Okay.
that room was a bit intimidating at first.
Yeah, so it became really gratifying for you.
Oh, of course, yeah, I love teaching.
Awesome.
And was there a like the hardest unit that you had to teach? Like for example, like was there a unit that you were teaching ever, not only this year, to students, and it was just very hard to explain? Was maybe a unit, maybe a concept? Was there
Hmm.
ever anything like that?
So at U of T, I've really only taught 137 as an instructor, and I would definitely probably say that the first introduction to epsilon deltas, and
Hmm.
then some of the Taylor series stuff, and so those would be the two main ones I think that are coming to my mind right now. Um, and just maybe some getting mixed up with dummy variables in the
Mm,
integration by substitution
integration. Yeah.
business.
I
Yeah,
remember
Yeah.
that.
yeah,
You were
I never
using
understood
the
why we
same
use dummy
letter on
variables.
two
yes,
different parts of the
yes,
board.
yes, yeah. That thing.
Yeah. So this next question is more of like an opinionated answer, I guess. But do you think that mathematics are discovered or invented?
Hmm. I guess um, human beings choose the axioms for mathematics, and then the rest, the math that comes out of those axioms would be discovered.
Interesting opinion.
Okay. So if you look at something like Pythagoras' theorem, it's
Hmm.
something that seems like super simple. Do you think that like humans were inevitably going to like, I guess in this case I'm kind of leaning towards it being a discovery, um or like a property of triangles that I guess that humans would like stumble upon, I guess, by experimenting. But do you think that it's something that was kind of inevitable for us to advance in mathematics?
I think so. I mean, like, I think that it's it's a nice philosophical question. Are you asking basically like, is it necessary to discover the Pythagorean theorem before proceeding to other things, or like is it a necessary step, or are you just asking specifically with respect to that theorem if it's discovered or invented? I would still say discovered for both, and I would say probably also that uh, it is probably necessary to discover that before you discover other things.
Okay, awesome. Yeah, my question wasn't super clear, but I was kind of asking a little bit of the two.
Well, it's okay. It was certainly more clear than that explanation of the proof I gave at the beginning.
So, what do you
Yeah.
think is? Oh, sorry. Were you
No,
saying
no,
something?
no, 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 no. I wasn't going to say anything.
Okay, so what do you think is like the most, or I'm not really wording this correctly, but pretty much I want to find out if there's anything in mathematics, especially, obviously, that is like we haven't solved it now, but if we do, if we can, it can really help our future. Is there anything like that in math? Because I know in physics, for example, there are like many equations, like the Millennium problems, where if we solve it, we can get a much deeper understanding of, for example, turbulence. So I was just wondering, is there anything like that, maybe in pure math, where if one were to solve it or do something to it, I guess some property of math will be fulfilled forever? Is there any equation like that?
Hmm, that's a great question. I guess it depends. I mean, certainly, like you mentioned, there are the Millennium problems, and like those would be like pretty high on the list for candidates of things like that. But also, you could ask any mathematician in any field, and they would definitely pick a problem in their field that they would say, yes, it would be amazing if this could be solved, because so many things would be true after that. I mean, the reality is that, like, if you take all the mathematicians at the department at U of T or something, or they all work in completely different fields. So sometimes some theorems would be helpful to a lot of fields, and I guess those would be the ones you're talking about in terms of being the most important,
Mm-hmm.
maybe in some sense, because they just would fulfill a lot of things for a lot of people, I guess.
So
Um,
in Cstar algebra, what
mhm.
is that one thing, or is there that one thing?
Well, yeah, there's this thing called the classification program where people are trying to basically understand exactly. So it's like it's basically trying to categorize things. So you have all these C-star algebras floating around in the air, and you want to understand when two of them are fundamentally the same. Like maybe they're the same in the sense that, like, I mean, maybe you have different labels for the elements in them, but fundamentally you can relabel them and they have the exact same properties and they're essentially the same. They're just named different things. So you want to come up with, I guess, a bunch of baskets to be able to put these C-star algebras in, so that when two of them are in the same basket, you know that they're essentially the same. But then you basically get to come up with the criteria for what it means to be in one of these baskets. So you want the baskets, you want to have enough baskets so that you can differentiate the C-star algebras. Like you could put all the C-star algebras in one basket and say we're done. But you want to have enough C-star algebras, you want to have enough baskets so that there's a meaningful difference between these groups, but then you don't want to have too many, so you have one basket for every C-star algebra,
Mm.
because then there's no point to the process. So you want to have enough baskets so that when two C-star algebras are in the same baskets, you can say something meaningful about those two that are in that basket, I guess.
So it's all about how specific you want to be.
Yeah, it's sort of like that, where the two extremes would be a basket for every C-star algebra, and then the other extreme would be one basket for all C-star algebras.
So well, I mean, we're coming up on
Coming up
30
on.
minutes now.
Mm-hmm.
So I guess that's everything.
I mean, I think this went pretty well. We asked a good couple of questions. I'm just
Yeah.
thinking if I forgot any questions that I was supposed to ask or that I thought of asking.
No,
Um,
I think I got everything.
okay, last question, Mihai. Last
Mm-hmm.
question, and I think this is really important. This will really define the future of this podcast.
No.
Uh,
Okay.
do you think that we were pretty awesome in your class? Like maybe one of the top students?
Well, sure.
Personality wise, of course.
Sure, why not?
Perfect. That's all I wanted to hear. That
That's
sounds
a
I
awesome.
mean,
perfect answer.
I remember both of you, and I remember exactly where you guys sat. So
Awesome.
yeah, I would say when I was doing my rounds, I loved walking by there.
Personally, I think I really understood that you legitimately maybe thought something for us, like actually thought of us when you pointed out that Parker had shaved his beard. I still
Hmm.
remember that day when you
Yeah.
pointed that out. I'm like, wow, this teacher actually cares about his students in a way that most teachers don't, because most people, even if they recognized it, they wouldn't really say anything. But
Hmm.
you did, and I was really impressed.
Yeah, I really enjoyed being in your lecture, and I could have switched to Rays, which was
Yeah,
more convenient, I think, but I don't know. I preferred being with a nice professor than having better hours.
I actually okay. I to be honest, I shouldn't really be saying this to a math professor, but I didn't go to a lot of the math classes that I was signed up for, and then Parker told me to come to yours and try it out, and that was just crazy. I
Oh,
absolutely loved it. No, I'm not even joking.
that's great. Thank you very much, guys. That's very nice to hear.
Absolutely. Once again, thank you so much for coming on this podcast. Thank you so much for a great year that you've had with us. Hopefully, we will see you again in
Yeah, I
the
hope
upcoming
so
year.
too. Yeah, thank you very
Yeah,
much for having me.
absolutely. Thank you so much. And that's Parker. You want to say something?
I was just gonna say it was nice talking to you, and Yeah, that's everything for today.
That's us
I'm
signing off.
Parker.
And I am Ray, and we bid you adieu to a fantastic day.
All right, bye.